All right, welcome back. In this video, we're going to start off by learning about some of the terminology that's used when we study anatomy and physiology. This is where, it's kind of like learning a whole new language. If you've ever taken, Spanish or French or some other language, you basically learn the terms first, and then you start to apply them. You start to use them. So it's not good enough to memorize definitions. You have to understand how to use these words. All right. So first we're going to start off with some of the positions. So when we study the human body, it's important to know what position the body is, because if you move the body, move the arms, move the legs, then things change their orientation. So typically when we're studying a human being, we study it as if it's in the anatomical position. So this is a standardized method of observing or imaging the body that allows precise and consistent anatomical reference. So, for example, if one person is studying this human being and the palms are facing you, you would say that the thumbs are lateral. All right, we're going to learn what lateral means, but it means further from this midline. But what if he turned those palms around? Then all of a sudden the thumb becomes medial. It moves closer to the midline. So in order to keep everything consistent, you usually assume that that body is in the anatomical position. So this is the anatomical position. So feet on the floor, palms facing the observer. So we're observing this human and the palms are facing us. Looking straight ahead. All right, so you're not looking to the right or the left. Your palms are not facing backwards or, towards the back, but this is the anatomical position. There's a couple other positions. Prone position is when the body is laying face down, maybe on a bed. And then supine position is when the body is laying on a bed, face up. So always kind of assume anatomical position. Okay, so directional terminology often comes in pairs that are opposite. All right, so why is this terminology important? Well, we want to be able to navigate throughout the body. We want to be able to explain where an organ is, maybe using another organ as reference. So if you know where the heart is, but you don't know where the thymus is located, someone might explain to you that that thymus is superior to the heart. All right, so it lies just above the heart. So we want to learn these terms by definition, but also how we use them. All right, and you're going to be using these terms throughout A&P1, A&P2. If you go into medicine, you're going to be using these terms. So it's important to work hard on these now. Okay, first pair is superior and inferior. Superior means it's above. All right, so it's kind of towards the head. It's higher up in the organ, in the organism. Inferior is below. It's going to be, further away from, the head, if you will. So on these drawings, you'll notice that they put superior is going to be above. It's going up. Inferior is going to be below. Sometimes we use cephalic. Cephalic means pertaining or close to the head. Caudal means close to the tail. But we're going to use superior and inferior quite a bit. The next pair are anterior and posterior. So anterior means you're closer to the front of the body. Posterior means you're closer to the back of the body. Other synonyms for this include ventral and dorsal. So ventral also means closer to the front. Dorsal means closer to the back. Sometimes we use anterior, posterior. Sometimes we use ventral, dorsal. You're going to want to know both sets. Next pair is medial and lateral. These words are used in reference to a midline. So this would represent the midline of the body, or it might be a midline of an organ. If you're closer to that midline, or closer to the middle of the organ or organism, you are medial. If you're further away from it, you are lateral. So for example, the thumb is lateral. Your pinky is medial. All right, and we're going to do a whole bunch of examples on the next slide. Next group are proximal and distal. These, the reference is an attachment site. So these are often used in arms and legs because your arms are attached at the shoulder and your legs are attached at the hip. So if you are further from the attachment, you are distal. Think of distant. If you're closer to the attachment, you are proximal. And then same is true in the legs. Your feet are distal. Your thigh is proximal because it's closer to the attachment. Next group, superficial and deep. The reference point is the surface of the body. If you're closer to the surface, you are superficial. If you are further from the surface, you are deep. All right, and that's deep is pretty self-explanatory. Don't mix up superior and superficial. All right, totally different meanings. All right. The next group, a little different in that ipsilateral means the two organs are on the same side of the body. So maybe you have an organ that's on the right, and then you have another organ that's on the right. Example I always like to give is your gallbladder and appendix. They're both on the right side of the body, so they are ipsilateral. Contralateral means the two organs are on opposite sides of the body. I like to use gallbladder and spleen. Gallbladder is on your right and spleen's on your left. They are contralateral. So these are some of the directional terminologies you're going to use quite a bit. Some we'll use all the time. Others we'll get to here and there. But the best way to understand and how to use those is practice them. So on this slide, I have some kind of fill in the blank where we choose one of those words. All right, and this is the kind of thing you're going to want to practice doing. Obviously, you need to know where some things are. We can't just, not know where anything is because then we won't be able to use directional terminology. So this is a good drawing showing some of the major organs, all right? And obviously some of these you know where your brain is, you know where your lungs are, you probably know where your bladder is. But if you don't know where the gallbladder is, now's the time to know, all right? It's right here, it sits underneath your liver, so it's inferior to the liver, and it's in this, what we call the right upper quadrant up here. So use this and just start to learn where organs are, because if you're asked about a directional terminology, but you don't know where the organ is, it's going to be very difficult. All right, so first one, the urinary bladder is what to the small intestines? Well, there's the urinary bladder. There are your small intestines. So the urinary bladder is inferior to the small intestines. If we were to reverse these two, and said the small intestines are blank to the urinary bladder, you would just reverse the term. You would put superior. Next one's carpals and metacarpals. So these are bones. And again, we're going to get to bones another day, but we should probably know where carpals are and metacarpals. Carpals are the 8 bones in your wrist. All right, so in your wrist here, you got 8 little bones called carpals. Metacarpals are in your hand. So your hand has 5 bones called metacarpals. So your carpals are here, your metacarpals are here. Well, the best word to use, because there's an attachment here, is proximal. So the carpals are proximal to the metacarpals because they are closer to the attachment site. Now, some people might say they're superior. And that seems like it's right, but it's wrong. All right, we don't use superior and inferior when we're in arms and legs. We would rather use proximal and distal. All right, so the carpals are proximal to the metacarpals. Therefore, the metacarpals would be distal to the carpals. All right, next one, gallbladder and liver. I kind of mentioned it previously. The gallbladder is inferior to your liver. So here's the liver. Your liver actually has 4 lobes. You can kind of see 2 of them here. This would be the right lobe. It's on the right side. So the gallbladder is just beneath that right lobe of the liver. Next one, trachea and esophagus. So the trachea is your windpipe. All right, so it's going to transport air down towards your lungs. So that's this tube here. The esophagus is for food. And notice that this is not in the anatomical position, but if you notice, your trachea is here. Your esophagus is going to be sitting behind it. All right, so the trachea is anterior to the esophagus. Your trachea is in front of the esophagus. One thing you might want to do is come up with synonyms. And then replace the word with the synonym. If it makes sense, then it's right. So for example, inferior, you could say below. Is the urinary bladder below the small intestines? Yes. Proximal, you could say closer to. Are the carpals closer to the attachment than metacarpals? Yes. Is the gallbladder below the liver? Yes. Is the trachea in front of the esophagus? Yes. Lungs to the diaphragm. So the lungs are superior to your diaphragm. Your diaphragm is a flat muscle. It's a respiratory muscle, so you need it to breathe. But it also separates your thoracic cavity from your abdominal pelvic cavity. So it's right here. It's kind of shaped like a dome. So those lungs are above that diaphragm. Gallbladder and appendix are. So notice this is a little different in that we're looking at the two together. Where are they? Well, your gallbladder is here. Your appendix is shown, you can't really see it. It's a little structure here. I just wrote appendix here. But notice they're both on the right side. So they are ipsilateral, same side. How about the radius and the humerus? Again, these are two bones. We'll learn about them, but it's never too soon to start learning about bones. Your radius is a forearm bone that runs right along this thumb side of your forearm. Ulna runs along the kind of the pinky side of your forearm. But we're not looking at these two. We're looking at humerus and radius. The radius is further from the attachment. So the radius is distal to the humerus. Fibula and tibia. So those are in the legs. Kind of like radius and ulna. They're right next to each other in the leg. But the fibula is lateral to the tibia. So the fibula is kind of on the outside of your leg, and then the tibia is on the inside of your leg. All right, and we're talking about below the knee there. In your thigh, it's the femur. There's just one bone here, the femur. We could use lateral and medial for these two as well, radius and ulna. The radius is lateral, the ulna is medial. So medial's closer to the middle or midline, lateral is further away from it. So the fibula is further away from the midline than the tibia. Brain is what to the skull? The brain is deep, right? It's further from the surface. Your skull is closer to the surface. Therefore, it's superficial. And then skin is superficial to everything, right? Your skin is the surface, so it's superficial. Ulna is medial. Again, closer to the midline. So we're comparing the two bones in the forearm. The ulna is closer to the midline, so it's medial. Pancreas to the stomach. So you probably know where your stomach is. It's kind of up here, kind of upper left area of your abdomen. Your pancreas, notice they're kind of showing it here, but it's behind the stomach. If we would have to remove the stomach to see the pancreas back there. So the pancreas, since it's behind the stomach, it is posterior to the stomach. So that's a good example, right? Maybe someone knows where their stomach is, but they have no idea where the pancreas is, and you have to explain where the pancreas is. You would say the pancreas is posterior to the stomach. Spleen and appendix are contralateral. So there's that appendix. It's on the right side. There's the spleen over here on the left side. So the spleen and appendix are contralateral. Now, someone might say, well, isn't the spleen superior? Yes, but it wouldn't make any sense in this statement. The spleen and appendix are superior? No, that doesn't make any sense. So it would have to be contralateral. So practice, practice, practice. Know the definition, and then be able to choose a word that completes that sentence. That's what I would recommend you do as far as studying directional terminology. All right, next one, homeostasis. Homeostasis, by definition, is maintaining or maintenance of a relatively stable internal environment. All right, so we want to keep things pretty stable, relatively. So it'll go up and down a little bit, but we don't want it to get too high. We don't want it to get too low. So this little graph here shows body temperature. You've probably heard the fact that our body temperature should be 98.6 degrees Fahrenheit or 37 degrees Celsius. But it can go up and down a little bit, right? It'll go up a little bit when you go outside and it gets hot out, or it'll go down a little bit when you jump in a cold lake. But we want to keep it relatively stable. So it can go up and down, but as long as it doesn't stay high for too long or go low for too long, we're in good shape. So think of equilibrium or balance or stability. All right. So how does your body maintain homeostasis? Well, it's got components. All right. It's got structures that help determine if that condition is high or low, and then it has organs that know what to do about it. So for example, when your body temperature gets too high, all right, how are we going to know? Well, we got to have receptors, all right? We got to have structures that monitor your body temperature, all right? So whenever we have a condition that goes out of the range, we call that a stimulus, all right? So a stimulus in this case could be high body temperature, or the stimulus could be low body temperature, all right? So that is a disturbance, all right? So homeostasis was disturbed. We have to be able to detect that. So we have structures called receptors. In this case, we have thermoreceptors. Thermoreceptors monitor body temperature. They monitor your internal temperature and they monitor your external temperature. So you got them in your skin and you have them in an organ called the hypothalamus in your brain. So we know what your body temperature is, we being your body knows. And if it gets high or low, those receptors need to notify a control center. So a control center is typically your brain, right? You probably know your brain controls a lot of what you're doing. So your brain's a good organ to, tell about this, right? So these receptors have to get this signal, and we use the nervous system, to get that signal to your brain, tell your brain our body temperature is high or low. Then your brain doesn't change your body temperature. It needs to notify an effector organ. So the effector organ is the actual organs that can change your body temperature. So the effector might be sweat glands, right? So when you have high body temperature, what happens? You got to tell your sweat glands to sweat, and that cools the body. If your body temperature is low, the effectors would be skeletal muscle. So now we can shiver and bring that temperature up. So the effector is going to produce a response that brings us back to normal, all right? Brings us back to maybe the set point. So that's typically how most things work in the body, all right? You got to have a receptor, control center, effector that produces a response, and then the response is going to bring you back to normal. Now, if the response is the opposite of the stimulus, we call that a negative feedback. All right, so negative feedback, we'll talk more about in a little bit, is reversing the stimulus, all right, to get us back to normal. So what are some other examples besides body temperature? Blood pressure. So same situation. If we have high blood pressure, we got to have a way to detect it. So we have receptors that are called baroreceptors. We got to have someone that knows, or someone to tell about it. That's going to be your brain, medulla oblongata, actually, of your brain. And then your brain doesn't change your body temperature. It would be your heart and blood vessels. All right, and we've probably seen these numbers, 120/80. That's kind of your normal blood pressure. The 120 is when it goes up, when your heart contracts. And then the 80 is when the pressure goes down, when your heart relaxes. So same thing, we could change this and put blood pressure, and same idea. We want to keep it in a relatively constant range. What else? Blood sugar. Same thing. We want to keep our blood sugar relatively stable. These are typically the numbers you'll see. Every book's slightly different. But 70 to 110 milligrams per deciliter is what your blood sugar should be. Now, will it go high? Yes, after a meal it'll go high, but you got to bring it down. Will it go low? Yeah, if you don't eat for a day, right, it's going to drop to 70 or even a little below. We got to have a way to bring it up. All right, and blood sugar is largely hormonal. So we're going to use hormones like insulin. You've probably heard of insulin to lower blood sugar. And then we've got one called glucagon, which will raise blood sugar. So notice that we might use nervous system to maintain homeostasis, or maybe we'll use hormones to maintain homeostasis. What else? pH. I mentioned this range previously. So we got to have a way to detect if our pH is too high or too low, and we have to have ways to get it back to normal. A lot of hormones need to be pretty constant, so we have to have a way to detect if let's say our thyroid hormones get too high. We have to have a way to bring it down. All right, there's some that spike. All right, some hormones will spike during the female reproductive cycle, but for the most part, hormones like to be relatively constant. Oxygen levels, carbon dioxide levels, electrolyte levels, fluid levels are all homeostasis. All right, so we want to make sure we understand the idea here, right? Maintaining a stable environment or internal condition. We want to know the components. What's a stimulus? What's a receptor? What's a control center? What's the effector? And what kind of response? But we're going to talk about homeostasis throughout A&P1 and A&P2. All right, negative feedback. This is kind of a complicated figure in your book. I like figures. I like taking my time and working through figures. I think they're very visual. It beats reading, right? A lot of students nowadays don't read, so books make figures, all right? So back in the day, there weren't any figures. And then publishers realized students aren't reading, so let's come up with another way to present the information more visually. So if you see something like this, don't panic and say, oh my gosh, that's too complicated. Just, it usually has little numbers. Just kind of walk through the figure, all right? And it beats reading. So what is a negative feedback? It's a system that reverses the change in the controlled condition. Said another way, it reverses that stimulus. So this example here is that temperature regulation. We're just taking it and looking at a little more detail. So basically, it kind of tells you where to start. So here's your body temperature, all right? It says homeostasis was disturbed by body temperature going up. So something caused your body temperature to go up, all right? Maybe you walked outside in the summertime. That's a disturbance. So we detect that high temperature, all right, using thermoreceptors. So that's the receptor, all right? We're going to, so notice here, receptors and control centers. So the control centers are in the brain. We're going to tell that brain temperature went up. The brain is then going to send signals to the effectors, sweat glands. We're also going to change blood flow. We're going to want blood vessels in your skin to dilate. That's going to bring more heat to your skin, and then we can pull that heat out using sweat. So your skin gets red. That's going to help us bring that temperature down. All right? Now, what happens if we start back here and we go this route? Now your body temperature drops too low. Same receptors, same control center. We're just going to change what the effectors do. So we're not going to sweat. All right? We're not going to send more blood to the skin. We're going to send less blood to the skin. And we might shiver and generate some heat. So this is a good figure to kind of understand the overall concept of homeostasis, the little steps that are necessary, and then this specifically revolves around temperature regulation. Positive feedback isn't as common in the human body. Most things work by negative feedback, all right? there's a few exceptions. In some cases, we don't want the stimulus to be reversed. We actually want the stimulus to be strengthened or amplified. And the idea of positive feedback is to get to an end point, right? There's an end game here. Temperature, there isn't an end game, right? You just want to keep it constant. But in this example, childbirth, there's an end game, right? There's the end game. We want to get that baby out of the uterus. And in order to do that, you have to amplify the stimulus. So here's the baby, right? The fetus. It's inside a uterus, all right? And at some point, we want to push that baby out. All right, and it comes out of a region of the uterus called the cervix. All right, so how do we do that? Well, at some point, there's pressure on this area, this cervix. All right, and that cervix has stretch sensors. So the stimulus is stretching of the cervix. All right, that stimulates neurons that send the signal to the brain. So now the brain knows that the cervix is stretching because this baby's big giant head is pushing on it. All right, oops, sorry. That stimulates the production of a hormone. The hormone is called oxytocin. Now we're going to learn this hormone in A&P2, but oxytocin stimulates the muscle of the uterus. All right, so now we get that muscle contracting. All right, what happens when the muscle contracts? It pushes that baby even more. All right, what does that do? It stimulates those stretch sensors even more and sends even more signal to that brain. All right, and then we produce even more oxytocin. And this amplifies and amplifies, right? We've probably heard of women having, contractions that get more severe, stronger contractions and more frequent contractions. That's because this amplifying of the production of oxytocin. Eventually, there's enough contractions to push the baby out. So that's an example of positive feedback, normal childbirth. Another example, blood clotting is a good example. Blood, clotting, there's an end game. Form a nice solid blood clot. So platelets kind of signal in more platelets. They kind of amplify the formation of a blood clot. All right, so those are good examples of positive feedback. Again, there's not a whole lot of them. Most things operate by negative feedback. Okay, so that's probably a good place to stop this video. In the next video, we're going to go over some regional terms. Not all of them, but just probably the ones you're going to run into soon. So we want to learn some of these regional terms now and maybe work on others later. And then hopefully we can get maybe to the end of this PowerPoint in the next video, or maybe we'll take two